Welcome to Graph Gurus 26, using graph algorithms for advanced analytics, part 1. So we're planning a 5-part webinar series where we're going to go through each of the 5 sections in our graph algorithm library. In this first one, we'll be doing an overall introduction to graph analytics, making use of graph algorithms. Thank you for joining us today. We know you're busy, sorry to keep you waiting, and let's go forward. So David? Yeah, so all the attendees are muted. If you have a question, please use the Q&A if you have a question about the content. If you have maybe some technical issue or a side question, you can, or want to ask the community, you can try the chat as well. But for the formal questions related to the topic at hand today, please use the Q&A and we will be answering those at the end. The webinar is going to be recorded, and in the event that we have some technical issues, we will probably internally re-record it, and then so that there will be a cleaner version to send out. So we always send out a recording at the end of the day or the next day, and we'll also be sending out the publishing the code for the examples we go through today. Okay, next. I'm Victor Lee. I'm the head of product strategy at TigerGraph. I've been with TigerGraph for about 5 years. My area of focus in my graduate studies was graph data mining, so I studied a lot of graph algorithms. My PhD thesis was developing a new algorithm, so this topic is near and dear to my heart. So with that, let's go right in. I'm going to be using today for the demonstration TigerGraph Cloud, where you can use the most scalable graph database as a service. You can get started very quickly on there. We've got a free edition that you can use. So after we're finished, if you haven't already looked, you should go to our main website /cloud, and you can learn all about it. So the outline for today, I'm going to give an overview of graph analytics and why it's so important for today's businesses. Then we're going to talk about graph algorithms. Graph algorithms, as I said, I studied in school. They've been around for a long time, coming out of mathematics, and then as soon as computer science became a field, it had resonance there. But why is that relevant to data analytics and graph analytics in particular? And after giving that general overview, we'll focus on the first area, shortest path algorithms, and then we'll do a demonstration in TigerGraph, in Graph Studio, and using TigerGraph Cloud. So today, one of the phrases you always hear is to be a data-driven business. Technology enables us to collect and store a vast amount of data, and that data can be so useful. It can be, if you can process it appropriately, if you can search it, if you can process it and gain insight from it. So having all that data, you potentially can see more, you can understand more, and then make better decisions. And not just, I want you to think not so narrowly about what people maybe typically call decision analytics, but realize everything you do in your job is a decision. You decided to do that. Why did you decide to do that instead of something else? So it's optimizing our activities. It is seeing new opportunities. Oh, I should start to do things this way instead of that way. Pursue that product instead of that product. All sorts of those choices we make, the big ones and small ones, throughout our lives. So that's why having that data is key, but then you have to be able to process it. That's why data-driven business is so important, because it's really the opportunity to do everything better. So next, and realize that when you're doing that data processing or data analytics, you are actually connecting data in some way. So all data processing is connecting data. The simple A plus B, that addition is a type of connection. Now it depends on how your data is stored, how you actually perform that. Structuring your data so that it's stored as a graph is a generalization, and actually it lets you, you're no longer limited to saying I can only do these types of processing. You're now merging your data, you are bringing things together so that you can apply whatever function you want to that unified data. So connecting data, it's about unifying without 100% merging. You're not turning it into one lump. Each entity still retains its identity, and it's that uniqueness of each identity and knowing how things relate to one another that in fact is the information you're looking for. So once you've even modeled it as a graph, you've already gained some information. And then when on top of that, you apply some algorithm, some query, some analytics, some machine learning, you're extracting even more. And fundamentally, statistical analysis and machine learning are about correlation. Again, it's that the core of that word is relate. So you have the existing relationships in the data, and you're trying to discover new relationships, which you could then persist in the data if you wish, or just have it as a streaming result, which you're using dynamically in real time. So it's a never-ending cycle of taking in data, seeing how it connects, and discovering additional ways of how it connects. And so graphs in this way are the ideal way to organize and analyze complex data. So I'm not going to go over this in much detail because we kind of already talked about this. I'm assuming most of you know what a graph is. I just sort of put this slide here to kind of reiterate why a graph is sort of natural, not just for modeling data, but for, and the modeling already is a form of information representation, and then there's the additional analytics you perform on it. And again, so have businesses been able to leverage graph technology already? Yes, it's a growing trend. Gartner predicts 100% annual growth from about 2000. I think they started this in 2017 through 2022. So we're still in a very rapid growth phase. And so we're going to tell you a little bit more about how graph algorithms play into developing your graph analytics. And why, again, the last bullet point, why did Gartner put this as one of the top 10 trends? Because it enables you to ask those complex questions across complex data, which it's not practical in traditional tabular data, and this is not to be overlooked, that just the fact that you reorganized it, there's always the human in the loop. We will see the data in a different way, and so that we will imagine different possibilities. And again, that's a loop. Once you imagine new possibilities, you can apply them. And so today we see certain set of applications. A few years from now, people will be seeing even more applications. So it's a really exciting phase for graph analytics. So graph algorithms. If you went through a traditional, excuse me, computer science education, then you probably covered at least a little bit of graph algorithms. If you had a data science background recently, you may also have covered it. But you probably at least covered algorithms. And so what are algorithms? They are, sets of sequences of instructions which do help you deterministically obtain a desired result. They take the form of functions where you give it some input, it crunches the data, and it gives you some output. And for graphs, they could be pertaining to the graph as a whole, or to some subset of it, some of the vertices, or some of the relationships. And so over the years, there have been hundreds of graph algorithms that have been developed. Some are more well-known than others. Some are, are more basic, have really fundamental purpose. So you can develop just like for, there are libraries. If you're a programmer, you know that you import libraries to perform all sorts of specialized tasks. So there are graph algorithm libraries, and TigerGraph has a graph algorithm library, and they become your toolkit, and they're also your building blocks. And it's sort of this dual aspect. So in one function, on one hand, they perform a function, and each one performs a different function. And so if you want to become a master user, you have to invest some time to learn, well, what is this tool for, and what's the right way to use it so I get the best benefit. And if you're doing any sizable project, you're going to use more than one tool. You're going to use a collection of tools. And in that way, that's why I say it's a building block, because each one is producing a result, and then it can be chained where the output of one becomes the input of another. And so it's that chaining aspect why you can also think of it as a collection of things, though the algorithms themselves construct your program. And you, with it, other things, it's not going to be 100% algorithms, but they become components of your larger application. So next, so for TigerGraph, our excuse me, our query language is GSQL, and our algorithm library is just where we have written queries expressing the functionality of some of these classic algorithms, and we've open sourced them where they're on GitHub. And so you can go to GitHub and see the source code. And also in our documentation website, we have fairly extensive documentation on how to use them, and with some examples. And the great thing about using GSQL is that you see the source code and you can modify the algorithms. I'm sorry, I'm talking a little bit too much for my own good. One of the good things for the condition of my throat right now, one of the good things about GSQL is that it's Turing complete. So, which means that any algorithm you find out there can be expressed directly in GSQL. You don't have to use a companion language like Python or Java or C++. You can do it directly in GSQL, which also means that it's going to execute directly in the graph database, which means you don't have to export the data. Some of the other platforms out there, they say they do graph algorithms, but what they're really doing is exporting the data outside of their database, which takes time and storage, performing the algorithm in another, sort of just directly at the system level, and then you have the result. And then if you wanted to update your graph with the result, that's another added step. So there's some overhead in doing it that way, but with TigerGraph, the GSQL, it is native. It's directly in the graph database. So next, and here are just some of the samples of some of the things, and over the course of this series, we'll be addressing each of these. So algorithms may seem kind of abstract and theoretical, and you're not sure how you're going to use this in your everyday real world use. So let's look at some use cases. So I'm starting off with some sort of abstract statement: which entity is most centrally located? And for any of these, it's a question of thinking, remembering, what does your graph represent? So does it represent delivery locations within your network, within your service area? Does it represent target persons, target organizations that you're trying to sell to or So in this case, centrality, you hear about when some chain, a chain store has decided we're going to open up a new store in this location. Why did they decide that location? And it's not just down to the city, but it's down to the street. It's down to which intersection. Why did they decide that intersection? Now you think, well, they just think about traffic that passes there, and also what type of traffic, like what's the demographics. You can transform that into a graph problem where that centrality, that's actually a case of betweenness centrality. They want to know how much traffic is passing through that area. That's betweenness. Closeness centrality would be more for like a delivery logistics, where do I put my warehouse? So that if I want to cover this area, the ability to cover, the average distance that I need to travel is going to be the shortest and the fastest delivery times, shortest traveled if I put my warehouse here. So that's addressed by this centrality analytics. How much influence does one entity exert over another? Market penetration, buyer influence. PageRank is actually a great algorithm for that. Which entities have similar relationships to a target entity? So I've got one case that's really interesting. Maybe I want to emulate that. Or this is a case of fraud or some kind of criminal activity. I want to see who else might be doing that. So you search your graph for that. So cosine similarity is a really well-known technique, which is not specifically for a graph. But when we talk about similarity in a few weeks, we'll tell you about a unique formulation that actually directly does leverage graph characteristics. And then there have been some algorithms specifically for graph, which have been developed for this sort of similarity detection. SimRank is one of the best known. RollSim is probably not as well known, but that was my dissertation. And then what are the natural community groupings? So partitioning or clustering your data into groups according to characteristics that you select. There are lots of different ways you can cut up the pie, which is the way that makes sense for you. And that's why you have to know different algorithms, because different algorithms can use different approaches for how to cut. So, the max flow min cut is one really well-known way. There's something that's been based on modularity, and it also goes by the name Louvain modularity community detection. There are lots of other ways, and so we'll go over those sets in a couple weeks. So lots of different real-world problems can be handled with graph. So if your data is already stored as a graph, or if you're thinking about what are the benefits if I decide to store it as a graph. This is just showing you some of them, and again, the purpose of this series is to help you see some of those and to help you to become a better user so you can select the right algorithm and to be able to deploy it efficiently. Okay, next. So as I said, how do you pick the right algorithm? You have to learn what each tool actually does. And again, because they're functions, they each need some inputs. So, and then it's not just what you think of as the inputs. The entire graph itself is an input. So sometimes the nature of what type of graph you have is relevant. Some algorithms are only for directed graphs, whereas every relationship has a direction from here to there. Others are designed for undirected graphs, where there's just a connection and it doesn't really go one way or the other. For example, friendship is often considered an undirected relationship. David and I are friends. It's not from me to him or from him to me. And some algorithms will work with either. So that's something that you have to know when you're trying to pick the right algorithm. The next step is also, how do you break down your problem, if possible, into a set of algorithms and other logic? Not everything is going to be a graph algorithm, but knowing how to deconstruct your problem, or and then reassemble it back together. That's sort of a skill and art form. It takes some practice, but through showing you some examples, we help you build up that skill. Okay, so here's one example. Here's an example. So say you're trying to find regions of influence. That is, you have a community in mind, and you believe that there are sort of natural groupings in here where there are certain leaders or influencers, and they will influence some subset. So you want to know not just what is the community, but so who are the influencers, but what subset of community will they influence? So in this case, what we're looking at is prescribers in a medical practice. And so when you have generalists and specialists, we're looking for who are the specialists that are the most influential. And what you have are referral relationships from general practitioners to those specialists. And then, of course, you have people just serving patients. So the idea is, if you have a lot, it's not just the number of referrals you receive, but it's the quality of referrals. Like sometimes there's a chain of referrals. So if you are sort of high on the chain, somebody received a decent amount of referrals, so they are influential, and they in turn refer to you because you received referrals from somebody who themselves was already influential. That boosts your influence, your authority. And if you know some things, you may have already recognized that approach as PageRank. That's PageRank. So in the next slide, I'm going to show you, okay, so you use PageRank to find who are the influencers. You can then use some various algorithms, community detection algorithms, to see who are they influencing. Now, of course, you could sort of back propagate to see who do they receive the referrals from. But you might actually want to use some hybrid data where maybe you're bringing in the patients, maybe you're bringing in the pharmaceuticals to see who they're influencing. And a lot of the community detection algorithms look at the density of relationships. So this might be a case where in the first stage you use PageRank to find out who are the influencers. And in the second stage, you use one of the link-based community detection algorithms looking at density of connections to find what are their communities. So that's just one example of sort of building an application or answering a more complex question by using multiple algorithms. And let's keep going. I've got a lot I want to cover. So now we are at breaking down some of the different types of algorithms. I came up with 6. You could come up with more if you want. The first one is search. We're not going to talk about that in detail. Again, if you have a little bit of computer science background, you've heard of breadth-first search and depth-first search. In our path search algorithms, we're going to be using breadth-first search. And that, in fact, is sort of the natural way that GSQL works. And the reason why is that's the one that takes advantage of parallelism. The TigerGraph platform leverages a lot of parallelism for its high performance. And so breadth-first search is sort of the natural way that GSQL executes things. So we're going to kind of take that as a given. And then we're going to start talking about path finding and path analytics today. And in the future, we'll be talking about some of those other topics. Okay? Now, here are just some of the questions you can ask and answer. So first of all, you can see with this small sample graph, 8 vertices, you can comprehend the whole thing. So when I ask the question, is there a path from A to H? You say, well, yeah, that's very clear. But of course, most of the time, you may not be visualizing your data. If you have 1,000 vertices, if you have 1,000,000, if you have 1,000,000,000, you're not going to look at it visually. You just want the computer to answer the question for you. And the path might be a lot longer than the 3 hops you see here. It might be 15 hops. So that's a valid question. Is there even a path? So That's called the reachability question. Once you know whether there is a path or not, then you say, well, how many paths are there? And that might be relevant because it may say something about what's the likelihood that a somewhat random traveler is going to be able to get from A to H, or what is the robustness or reliability? If this is a communication network, if one of them breaks down, is there still a way? What's the degree of separation? The smaller the degree, the greater the influence. This has a lot of real world applications. This has even been turned into games. You make 6 degrees of separation. We even made a movie about that. The Kevin Bacon number. How many hops is it from one from one actor or director to having worked with Kevin Bacon? You can actually click on that link and you can play around with it yourself. I think we'll skip that today. If I were running this myself, I would do it. Sorry, but go to oracleofbacon.org and play around with it. Let's go on the next slide. So, and just to let David is helping me out with the presentation today. There are animations here, so we are going to be clicking through this a couple times. Oops, I think we can go back. Yeah, sorry. What is the shortest path? Again, so 2 fundamental questions we can ask and 2 different types of data. So what's the shortest distance? And then what is the actual path? So I might say, okay, well, the distance is 3 hops, and that's the answer. The answer is 3. But maybe you want to know what's the actual path. Oh, okay, the path is maybe A to B to E to H. Or there's also a path A to C to F to H. So we're going to look at the first case with an unweighted graph where we're just counting the number of links. Okay, next slide. And I'm going to very quickly walk you through the algorithm. Some of you will know this, but again, this kind of puts us all on the same grounding. So in unweighted, the technique's really simple. It's just breadth first search. So as a side benefit, you find out not only the distance from A to H, you also find the distance to several other vertices that were along the way. If this were a function, you might write it as shortest distance unweighted with 2 input parameters, the source and destination, and the output would be 3. So if we click once, you'll see that what we do is we see that, okay, in one step, it sees that the distance to B is 1, distance to C is 1, distance to D is 1. Yeah, sure. Another iteration, another click, we see those are 2, and one more iteration, we see those are 3. So nothing surprising there. Some of you may know that you can actually improve the performance of this algorithm by doing bidirectional search, by searching both from A and from H and looking for where do the 2 paths meet each other. And that can significantly reduce your computation time on a large graph. But I just didn't choose to show that here. So next, let's say you actually wanted same graph, same basic question, except you actually want to know the path, not just the number of hops, but the path. So in the first click, first hop, what you'll see is we label, instead of labeling it just 1, we label it with A. That is, I got to B from A, duh. It's just 1 hop. This doesn't look very interesting. It looks more interesting on the next one. So it's, okay, how did I get to E? I got to E from A via B, etc. And how did I get to F? I got to F from A through C. And one more, then you get on G, you have that path. Now notice on H, I've recorded 2 paths because I approached H both from E and from F. So there are actually 2 solutions there. And so if you ran this as a function, one more click, what you'll see is that what you should get is this function where the output is a list of lists. So each item in the list is a path, and so it's potentially multiple paths. Okay, so that's an unweighted graph. Now let's look at a weighted graph. So I'm using the same data, and I've added weights here. And so looking at this now, let's just look on the left. Getting to C, A to C. There's a direct route from A to C, but that's not actually the shortest one. The shortest one, you go through D, go A to D to C, because that has a weight or a total cost of 3, whereas the direct connection has a total cost of 4. And just think about airline routing, where sometimes that nonstop ticket is more expensive than the ticket where you make a connection. And that happens to me a lot, so, and you all know that. And we're gonna do an example later with airline data. So next slide, please. So same thing. And again, there's a very classic algorithm named after the well-known computer scientist. Oh, I forget his first name. I want to say, I forget Dijkstra's, Edgar, something like Edgar Dijkstra. He did a lot of important contributions in the early days of computer science. One of them was this classic algorithm for shortest path distance. So to outline the basic procedure is, what you do is you start off with an initial assumption that the worst case scenario, that it takes infinite time to get from A to any other vertex. And as you proceed, you're going to incrementally reduce the worst case number. As you see an actual path, you say, okay, I found a path, so that means I know I actually can get here in that much time. But you need to keep going because you might find a better path, right? So in that first, for example, in that first iteration, you'll see that you can get from A to C with distance 4. But you don't know that's the best answer, because we can see that if you allow 2 hops, you'll be able to get from A to C with only a cost of 3. But you won't know that yet until the second hop. So it works by every step you find a better estimate. There's one little important detail, that each round you have to start with the best known, the shortest paths known so far. So if we go to the next slide, we'll again walk through the data set. So here's the initial data set, and notice I've tagged some of them with infinity, and you don't see it on the first, because this is showing the first iteration. So if we click, then we see on that first set, one iteration tells me I can get to B with distance 2, and again from A. So and if you go to the second iteration, you'll see that okay, I can get to E with a cost of 4, and the path is A to B. Notice C. This is what we talked about, how you update the answer. After just the first iteration, the best answer we had was distance 4 directly from A. After the second iteration, we can now say distance 3, path AB. And I got that by going through first the AD and then the DC. So we're reading the information that was stored on D after the first step. So we took the 2 and the A, we added 1 to get 3, and we added D to get AD. So that's 2 iterations. On the next slide, we see the third iteration. Next slide. Oh, okay, yeah, that was it. Sorry. I think. Oh yeah. So 1, 2. Oh, right. There was more here. So we're still on the second iteration. So the reason why we actually had to process some of the data first. So going from the first iteration on the left to the second iteration on the right, there were three nodes that we had to process. We had to move forward from B, C, and D. And we did B and D first before C. It's important that we do B and D before we do C. And the reason why is for exactly what we saw. Doing D actually changed the answer for C. That's why you want to defer doing C. And so what we're showing now on the right is, okay, now I've done it all. I've completed the second iteration. So I now have answers for C, E, and F. And that answer for F depended that I process D before I process C. That was why I broke that down. Okay. If you didn't get it, that's fine. It's all in the algorithm. It's all in our GSQL. So next slide. And just showing you, okay, this is pretty much at the end. We do node E first, which gives us answers for G and H. And we click one more time. We're still in the third iteration, but now we're doing F. We're doing F after we did E. We previously had an answer for F, but we've now updated it. And we now see that there are two ways of getting to F. There are two ways of getting to F with a cost of 6. And the last iteration, we actually have already, after 3 steps, we reached every graph, I mean, every vertex at least once, but we had not traversed every edge. So we still need to try a couple more cases to see if we can lower any of the numbers. So if we click one more time, we'll see that we actually do lower the number for H. So that means that there are at least 3 ways to get to H. There's actually a lot more than 3. But there was one way that had a cost of 9, and there are 2 ways that have a cost of 8. And so that is the full algorithm. So that is pretty close to what we were going to show you in slides before we do the demo. I do have some summary if you go on to the next slide. So reviewing, graph algorithms answer fundamental questions about connected data. And each of those algorithms in a library is like a tool in a toolkit. And it's also a building block for answering more complex business questions. Notice that when we had 2 different types of graphs, an unweighted versus a weighted graph, we still solved the problem, but I used 2 different algorithms. And you could have actually used the Dijkstra's algorithm for the unweighted graph, but you probably saw it was more complex. And that complexity turns out, it translates into performance. And these are the best known theoretical solutions. So TigerGraph's advantage in performance is our implementation of no vendor out there can tell you that they can do it in fewer fundamental operations. There are theoretical limits. But there are differences in how those steps are performed. You know, TigerGraph performs those steps more in parallel. And there also are sort of real world differences on how long does each little micro step take. That's just efficiency of software in general. So TigerGraph does have we are the highest performance platform in a lot of cases, but we cannot break the laws of physics, cannot break the fundamental laws of mathematics. Betweenness centrality will always be a slow algorithm on very large graphs. So that's another thing you need to know as a smart practitioner. And lastly, next slide, there are a couple of practical software issues. Let's just jump to the slide after that. And this is just, again, so these are a lot of things that you may want to look for in a practical solution. You can call each algorithm either as a function call or use it as a RESTful endpoint. We run the algorithms in database, so you don't need to export the data. You can update the graph. You can modify or customize the algorithms because GSQL is Turing complete. And the platform itself has massively parallel processing. And Next slide. We were finally ready for our demo. So the question here is whether that's actually going to happen today or not. And that is where I see if Kevin Tsai, one of our solution engineers, is ready. Looks like he is. Kevin was actually going to help. The original plan was he was going to help me present, but he kind of has a sore throat and lost his voice, so chose not to speak today. But if we go to design schema, I told you we have airline data. So we have a bunch of airports, and you can see they've got several ways of identifying them, and then flight routes, which go from one airport to another. We got this data from, I think it was called openflights.org, where it had something like 8,000 airports and 60-some thousand routes all around the world. We got that data, we downloaded it from their website in CSV format, and we just imported it. And this is our handy visual way of mapping data from CSV files into your graph. You can see that the data file, the CSV file, where Kevin's kind of got the arrow hovering there, you can see the various columns. I took source airport, and I combined that with the source airport, I think IATA code. I concatenated them together to make the ID that I use in the airline routing. And the reason why I concatenated them, actually the first part there, the first of those two parts is the IATA code, which you probably, like, the abbreviation for San Francisco Airport is SFO. The Open Flights database, they also use their own IDs. And the reason why we added that is because there are some smaller airports which are included in their database, which don't have IATA codes. So I wanted to put that first because it's the most recognizable, but to make sure I had a complete solution which covers every airport, I had to also include something else, so I included their own ID code. So anyway, that's how that works. If you go to the next tab, that'll just sort of summarize for us how big the data set is. So if you look on the upper right, you see, yeah, there's almost 8,000 airports. And after eliminating some duplicate routes in their database, because they also track by airline, and I wasn't interested in looking at which airline, I just wanted to see, is there a way? So after eliminating sort of duplicate ways of getting from A to B, we ended up with some 19,000 unique flight routes. Okay, so finally, Explore Graph. We're gonna do this fairly quickly. We've still got 13 minutes. So we've got some data displayed here already. We can call up some new data, okay. So you see the identifiers on them. Again, the code, PEK in the center, Peking or Beijing Airport. Now we are seeing, it looks like we're seeing about 20 connections. Now I know for a fact there are more than 20 non-stops out of Peking. It's probably because when he did the exploration, he put some filter on it. But you can also see, if you hover, actually, if you go up to the settings at the top of the menu, the gear, and then I want to change the settings on the flight route edge. Show miles, but don't show type. Great. So then we'll just see these distances. And so these are all non-stops. He's got like one indirect route shown there, but these are mostly non-stops. So is that Nagoya there? That's 869 miles. At the bottom is EWR, that's Newark Airport, just in New Jersey. So it's a nonstop of 6,800 16 miles. Now, we're not showing you the algorithm yet. We just want to show you like what is the data we're working with and for you to get some feel for it. We did not, the data that OpenFlights provided did not have the mileage. It had the latitude and longitude location of each airport. So we actually had to calculate those distances. And Kevin can show you the query he used to calculate those distances. There is a standard formula for calculating distances, but it's not your standard Euclidean distance because the world is not flat. The world is a globe. So there's a lot of trigonometry involved. You can see those sine and cosine functions. This may look like Java or C or Python or whatever. This is GSQL. And that's why we're saying it's actually, GSQL is Turing complete. It's really easy to implement a lot of algorithms. So what this does in brief, I'll kind of skip the line that says start equals airport dot star. That says we're going to consider every airport. And then the next line, we are iterating, we are selecting that pattern. So from start, from any airport across any flight route to any other airport. So it's really covering every route. And then, so for every pair of airports, you know, from an airport to another airport, apply this formula using the latitude and longitude of the source and destination. And then the last line in there, it says e.miles. So E was the name of, E refers to the edge that connects those two, source and target. And it has an attribute called miles. And that is basically the result there. The C was the result. R is scaling it according to the diameter or the radius of the Earth. And that's the answer. So we're computing this value, and then we're actually updating the graph with the answer. And so just for that one function, that one query puts the mileage on every edge. So let's move forward. Let's show you shortest path. So let's go to shortest path, no wait. And let's just, in the interest of time, we'll just sort of do each one of these one time. If you got some, yeah, you need your dash in there, right? So if you look up what is CNX, I'm looking at myself. I don't know what it is. It's Chiang Mai in Thailand. So it's actually computing the distance to every other airport in our data set. And it's not showing you the results visually because that kind of wouldn't really make any sense. But if you look at the JSON results, so just the first one, again, these are not sorted in any way. It's covering every airport in its data set. So remember, all of these are starting from Chiang Mai Airport. You can just pause on any one of them. Let's see that. That's kind of weird. You can see where it's got that //n in the name. Some of them had weird names. So XIC Airport happens to be Xichang Qingshan, which is somewhere in Sichuan. Not necessarily a major airport, but if you wanted to go there, you go through CNX, then to CHG, then XIC. Now, the way the algorithm is written, it finds one path. So that excuse me, that connection is 2 hops. It's possible there are other 2 hop paths. There probably are. The algorithm is designed to only report one. Say you want to know all the 2 path solutions. Well, actually, it turns out we do have a built-in feature, which we can show you later. Because shortest path is so common, that's actually built into the Graph Studio platform. or you could modify this algorithm. And that's one of the great things, that you can modify these algorithms. And we'll probably cover that in another one, how you would do that particular thing, or maybe do a little just blog. But let's show the other algorithm, positive weight. This algorithm, we actually did not use the Dijkstra algorithm. And the reason why is, if you remember, I mentioned that when you process Dijkstra, you have to always do the shortest known paths first. So because that one might actually update the answer of some of the other ones that take a longer, that are a further distance. That does not allow parallelism. So there are other algorithms which use parallelism for finding shortest path, and we used one of those. So I also added a couple other parameters to the query, maximum number of hops and maximum number of destinations. That's the size of the output. So instead of reporting all 8,000 possible destinations, I want to limit it. It's not limiting the calculation, it's limiting the final output. And that just makes it, and I added sorting into this. And you'll actually, yeah, if you look at the code right there, see a couple comments, sort vset. So those 4 lines from where it says vset equals select s down to the limit, I just added that so that the output result is sorted. And you probably recognize the order by and limit from SQL. That's showing you how similar G-SQL is to SQL. And adding that's where the max destination limit is used. The max hops destination is used a little bit higher. We have a while loop. If I did not have if I put a really big number here, then it would, this algorithm does n-1 iterations, where n is the number of vertices. But realistically, I don't want to take an airline route that's more than, say, 4 or 5 connections at the most. So realistically, I don't really need to search until after, say, 4 or 5. So let's run this algorithm. Again, we could start from the same airport. And we can set the hops to 4 or 5. And we could set the destinations to say, oh, let's do 1,000. It's not really a performance thing. It's really just so the output is sort of human comfortable. Now, notice the very first result is showing I think going to itself. Going to itself has 0 distance. Yay. Going to PYY, 55 miles. So there's several airports that it goes to directly. And these are all actual routes. They're serviced routes. These are not just calculating what's the theoretical distance between these 2 cities. It's only using actual routes in the graph. So keep scrolling down. I don't know how many more nonstop routes we have. When do we start getting, okay. Starting to get to some, we still have nonstops. Well, I guess Chiang Mai has a lot of service. Another thing, if you could actually scroll down to the bottom of the list, if you go to the scroll bar, yeah. So, why is that path? Oh, I'm sorry, I'm misreading this. Yeah, it's not this is not a nonstop. But if you look at that last one, so it's starting at Chiang Mai to Bangkok to Antananarivo, Johannesburg, and somewhere else. So if you wanted to go to that last city there, it would take 1, 2, 3, 4 hops with a total distance of 6,176 miles. So that's showing an application of we actually just directly used the algorithms. We didn't really turn them into fancier apps. It's just showing that in some cases, these algorithms can do useful tasks. So yeah, I've taken up the entire hour. Let's see if we have any burning questions. Somebody else, if one of my companions can call out for me any questions. We're happy to go a little bit long today. We don't, if you need to go, we understand, and we thank you for joining us, but we're going to keep running so we can answer some of your questions.
Victor, it's David.
Yes.
That was excellent, excellent presentation.
Thank you.
And good recovery from the technical issues we had at the beginning. We do have quite a few questions, several actually. Here are a few from the audience so far. One is, how many algorithms do you support?
So currently, we have about 25 or 30 in our library. And you can go to, if you go to our main website, first of all, our documentation website is docs, docs.tigergraph.com. You can find it there. We also, if you search on GitHub for GSQL graph algorithms, you could find it there. And for each one of those, we offer some variations depending on how you want the output. We offer some different operations. The way we've actually structured it is there's one main template algorithm, and then we have a little config/install script, which you can run, which will spit out variations of that algorithm based on what sort of data do you have, how do you want your output, etc. We're always adding more. So I said we have about 25 or 30 now. If you have some requests, send us a message, and we'll see how soon we can get that one out.
Great, thanks, Victor. Another question is, do you have a training class/guide? Do you have a training class/guide for customizing algorithms?
So we're hoping that this webinar series actually will do some of that. The examples that we very quickly showed you today, these are actually slightly enhanced versions of what we have in the graph algorithm library right now. So actually, if you could wait a little for these to become available, and we're also going to be updating the algorithms that are actually in the library. So if you, everyone who signed up for the webinar will be getting an email follow-up from us. And so just in the next day, so we'll have those new ones available. And those will include some notes on what were some of the customization tweaks we made. And we'll do further examples. And as we complete this webinar series, you know, it is being recorded. They're all going to be public, and we'll probably refine it into a training course like that.
Okay, great, thanks. We'll do a couple more questions. We do have several. We'll do a couple more. How do I embed an algorithm? How do I embed an algorithm within an app?
Yeah, can we switch back to the Graph Studio? Is Kevin still there? Like I said, there are two ways. You can include the GSQL code directly in a larger GSQL program. We do allow that each query is like a stored procedure, so it becomes like a function, and you can have queries calling other queries. But they also create restful endpoints. So if you can show us the restful endpoints, right? So after you compile this query, this is for shortest single source positive weight. That little snippet of code there is the signature to call this endpoint. So if you're writing in whatever language you're working in, if it has an HTTP library, you can find online, how do I incorporate RESTful endpoints into my application? You can do that. So those are the two ways. Do you have like one or two more?
Yes, we have several more, but I think in the interest of time, Victor, we'll just do one more question. And that is, I know other graph databases have algorithm libraries too. How is yours different or better?
Right. Well, it's definitely different, and I will tell you it's better, and you can judge for yourself. I did go over some of the things before. So our algorithms are written in our language, GSQL, which I'll be able to spend more time in upcoming webinars where we'll look at the code, and you'll see how similar it is to the high-level pseudocode that algorithms are often written in. So there's very little work involved in translating a generic algorithm in pseudocode into GSQL. The fact that it is open source and written in that language accessible to you is another key difference. Some other platforms provide only embedded functions where you can call it, but you can't see their code. You don't know how it's running, which if it works, it works. That's fine, but it means you can't modify it. And I said, just for the purposes of this demo, I made 3 modifications to that algorithm. I put in a parameter for maximum number of hops. I put a limit on the output, and I sorted the output. And because I'm familiar with GSQL, that took me like 10 minutes. But again, in the notes that we're going to send out, I will call those out to you. And I think you'll see that you could have also very easily done that. So that's another key difference. The platform on which they run. TigerGraph we are massively parallel processing. Other factors that lead us to be the most scalable. You're just going to get higher performance, and the fact that our algorithms run in the database, it's not running. We're not exporting it onto the server or onto Spark. It's where your data is. So it's following the idea of processing data where it resides. So I'd say those are the key differences.
Awesome, thanks, Victor. I think at this point we'll wrap up the webinar, but I wanted to give a big shout out to Sonia. Thank you for the multiple questions you submitted. We will respond to you, Sonia, by email, and we'd love to chat with you on the phone. And also to, I think Maxine is how you pronounce that person's name. Thank you for reaching out. And also to the anonymous attendee. I'm glad that you were able to stumble across this webinar. We do webinars every week. Victor will share some information about upcoming ones in this series. But to the anonymous attendee, if you can go to our website and register for one of the webinars, and you'll do that under the resources tab, which is the 3rd tab from the left. Once you do that, you'll be in our database. And so when we send out information on upcoming webinars, you will also be included on that information that we send out. And I think that will address the issue that you had. So I think, Victor, I recommend we wrap things up. We still have over 30 people on the webinar. So should we move forward with the slides?
Yeah. So thank you. I think you could even let, this is just our general way we wrap up every webinar. If we have a developers forum, I think in an upcoming forum, we'll want to introduce you to our new developers and technology evangelist, John Herkey, who is really doing a lot of things to establish a stronger responsiveness and bond with our community of developers. So, but we have had this developer forum available. We have office hours where you can chat with our developers every Thursday. So those are programs that are ongoing and a great way to reach out to our technical gurus. Next, I said, the demo today was using TigerGraph Cloud. It's very easy to use, and you can try it for free. And we also have a test drive where we have a couple use cases which are already loaded, and you can play around with those. If you'd rather download the product, you can do that. And we have a developers edition, which is very high powered. It's really the same engine as the enterprise product. And these the slides, well, at least the examples we use today are going to be added to our GitHub presence, and that is showing you that's our GitHub address.